Hey everybody, welcome back. This is chapter 12, section 5 in our calculus Anton book, 11th edition. This section is on curvature and the radius of curvature. We've been working in vectors with vectors and looking at the tangent line, binormal line, and normal lines. Here we're going to take a look at the curvature. So let's look at how the tangent line is affected by arc length. If I've got a straight line like I do here, when I say the tangent line affected by arc length, I'm looking at the magnitude of dt ds. Okay, we know that the length of tangent is always 1. So what we're really looking at is what direction is dt ds heading in. A straight line, the tangents are the same, so the tangent line isn't changing. If there's just a slight curvature, then we've got, it's just the dtds, the absolute value of that is just a little bit above 0. And then if we're sharply curved, this is going to be quite a bit above 0. And so dts, since it's got a unit length, it's just measuring the change in direction. Like how much is it changing in direction? There's no change here. It's changing slowly here. It's changing rapidly here. Okay. So curvature, we use kappa. Kappa is the K. And it is the magnitude of dtds. And we saw that that is equal to r double prime of s in 12.4. And I brought it up at the end of 12.4. So we'll take a look at that. And for circles where K is for circles, kappa is kept constant. But for other curves, it's going to change, and we'll take a look at both. Okay, and see how they connect. It's kind of cool. So let's take a look at an example. We're going to use r of t equals rho cosine t and rho sine t. This is going to be a circle of radius rho. I'm deliberately using rho and not r because our vector function is called r. So to avoid confusion, we're using rho. So if we take the derivative, we're trying to get this double prime right here of s. We need to first convert to s. So if we take the derivative and we treat it as u, then we can find the arc length. So negative rho sine u and rho cosine u. We take the magnitude of that. The magnitude of dr du is what we put into our arc length formula. And that should have a du right here, and it doesn't. Should have a du right there too. So we plug in negative rho sine u, we square it. We plug in rho cosine u, we square it. We add them together. Rho squared factors out. We're left with sine squared u plus cosine squared u. We all know what happens with that. This is a familiar song at this point. That goes to 1. We've got the square root of rho squared, which is just rho. It's technically the absolute value of rho, but since rho is a radius, it's already positive. We don't need the absolute value signs. So we're doing the integral of rho du from 0 to t. And that's going to get us that s equals rho times t. So t equals s over rho. So now we are going to change r of t to r of s by making the substitution. Okay? And we're going to take the first couple derivatives because that's what we need. We need the magnitude of r prime. So we do that here. I make the substitution first. We've got rho cosine of s over rho and rho sine of s over rho. And each time we take the derivative, a 1 over rho is coming out from the chain rule. So the first time, the rho and 1 over rho cancel. And the second time, we are stuck with a 1 over rho that doesn't cancel with anything. So r double prime of s is negative 1 over rho cosine of s over rho sine of s over rho. And you don't have to factor it out. I just did for illustration purposes. We now need the magnitude of that for kappa. We take the magnitude of it And we see we get our same familiar sum, sine squared and cosine squared, that equals 1. We're left with the square root of -1 over rho squared, which is 1 over rho, which is constant. The radius of a circle is constant, so 1 over rho is constant. That's kind of neat. And that's what I had said earlier. Kappa is constant for circles. And we just showed it right here. Because this equals kappa of S. Okay. Next thing we want to take a look at. I would agree with you if you were thinking, I don't like shifting to arc length, it sucks. I agree, it's more work, but sometimes it makes our lives easier. But if we just want to find the curvature, we have a shortcut. And it's dependent on ds dt equaling the magnitude of dr dt. And that needs to be a vector. So if I treat k kappa of s, we had earlier said it's the magnitude of dt ds. I can rewrite dt ds as dt, d-tangent line dt times dt ds. And if I do that, instead of multiplying by dt ds, I can divide by the reciprocal. That's what we do when we go up here. So now I've got d tangent dt divided by ds dt. And we just got done saying, reminding you up here that ds dt is the magnitude of dr dt. Now our top is the magnitude of the derivative of the tangent, and the bottom is the magnitude of the derivative of the position vector. So we can write kappa in terms of t if we have the magnitude of t prime over the magnitude of r prime. Okay. There is another way to get kappa of t in a different format, in a different form entirely. And I'll show it here, but I'll make the derivation of it in another video. For you, those of you that don't care about the derivation, you can just see the formula. Those of you that do, you can watch it. The other format is the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. Okay, so we've got a couple ways we can look at kappa in terms of t. We've got double prime of r in terms of we do s. So we've got a couple ways to find this curvature. So let's do another example. We're going to find the curvature of r of t at t equals 0, and we're going to use r of t equals e to the t sine t, or e to the t sine t and cosine t. So I calculated r prime and r double prime first, and I get these two vectors, e to the t cosine t and negative sine t, and then e to the t negative sine t negative cosine t. In an interest of saving paper, I threw together my cross product right there by putting an ijk above it and putting the little cross product lines. So we're going to do r prime cross r double prime right now. So we do the I component, we get negative cosine squared minus sine squared. And then the j component, remember it's negative. We get negative e to the t cosine t plus e to the t sine t. And then for the k component, we have negative e to the t sine t and minus e to the t cosine t. Okay. Cleaning that up, the first one, if we factor out a -1 on the I component, we have cosine squared plus sine squared. We are back to the good old -1 there. For the j component, I distributed the negative, and then I factored out the e to the t for our demonstration purposes, or for writing it down. And then our k component, they both have negative e to the t, so I factored that out. That's our r prime cross r double prime vector. Prime of t cross r double prime of t. So we're trying to make this kappa right here. We already have r prime, so we can take the magnitude of that and cube it. We can take the magnitude of this vector, and we'll be good to go. So doing the magnitude here was straightforward. I could have plugged in the values first, but this bit is going to show up more than once. We have a couple other problems like it, so I want you to see it. So squaring each part, we got 1, and then e to the t squared is e to the 2t, and then we have the square of that parentheses and the square of that parentheses. So do not distribute the squares and just call it quits. That's not how squares work. Remember, it's 2 parentheses multiplied together. We got to multiply it all out. So cosine t, negative sine t will get us a cosine squared minus 2 sine t cosine t plus sine squared t. That's this parentheses right here makes up that portion right there. And then we get our other section right here, cosine t plus sine t squared gets us that portion there. The negative 2 sine t cosine t cancels out with the positive one. And I'm left with cosine squared t plus sine squared t, that makes 1. And then another cosine squared t plus sine squared t makes another 1. So I got 1 plus 2e to the 2t in the radical. We're almost done. Let's bring it home. So I rewrote that value up here, 1 plus 2e to the 2t, the square root. I wrote down the magnitude of r prime. We have the square root of e to the 2t plus cosine squared plus sine squared. So that simplifies to the square root of e to the 2t plus 1. It's almost identical to the numerator, right? If we write it as this over this cubed, but this has got a 2 in front as a coefficient. This doesn't, so we can't cancel anything out. That should say an e to the 2t right there, and it doesn't. So we have r prime cross r double prime on top, the magnitude of it, and then we have the magnitude of r prime on bottom cubed. So that's kappa of t. If we want to find kappa of 0, it's plug in 0. We got 3 on top and 2 on bottom in the radical, and it's cubed. So square root of 2 cubed is 2 root 2. And this will clean up to 6, square root of 6 over 4 if we just multiply the top and bottom by root 2 over 2. That's it for this video. Stay tuned for more.